Okay, it's my great pleasure to welcome Ziyun Wang today to the presentation in our frame of the International Online Seminar on Interval Methods in Control Engineering. Our speaker today has received his PhD degree in control science and engineering from the Jiangnan University Wuxi in China in 2015. He has passed several international research stays, and those were in the US and in the Republic of Korea. And currently he's performing research in the area of filtering methods with applications to fault diagnosis, system identification, and state estimation. And now I'm handing over the microphone to today's speaker. We're looking forward to your talk.
Okay, thank you, Andreas. And it's also my pleasure to share this talk with the researchers in the Senate membership filtering field. And this title of this talk is Vector Set Inversion Interval Filtering Based Fault Observer Design. The Senate membership can also used in the state estimation, system identification, and fault diagnosis or fault detection. And this talk has 5 parts. First, I will give some introduction about this talk, and then we talk about one linear system and its transformation. And then we design an interval observer and give a simulation example. The last is the conclusion of this talk. In this set membership filtering research field, some feasible set can be obtained to wrap some different variables that include state, measurement, output, and disturbance or noise term. Some different geometries can make this feasible set, such as interval, ellipsoid, zonal top, parallel or the orthotop. And so in this figure, we can have 4 typical geometries, such as the interval or the cube. If we just draw this interval in 2 dimensions, that will be a box. And the other one is the ellipsoid, and the zonal top and the parallel top. In the set membership filtering field, we commonly assume that the disturbances and noises of the researching system are unknown but bounded. Or we can say this is a UBB system or uncertainty system. And we can animate errors caused by inaccurate system models. The computational complexity is one index that we find a novel set membership filtering method. And the filtering method can be widely used in signal processing, fault diagnosis, or robot and other fields. Then we usually design some observers. In this talk, we design the interval observer, and in some other papers or research works, we can find some other observers such as the zonal top or other geometries. And one thing that we make research before, we should know the system is stable or not. So the first thing that we have to do is to test the system. So some common design methods include coordinate transformation and flow placement. And the commonly used one is the LMI method. Also in this talk, we use the LMI to make the system stable. Okay, the common way is to find a fault-free system, and the other system is the actual system. We compare the output and the observer output to design observer gain and make it into the fault-free system and obtain the error. And then we test an error is converged into 0. Another index of the set membership is the wrapping effect. If we use the interval method, we can see if we just, for example, in this figure, if we see this one line, and it will become to an interval, and with the time increasing, the intervals will change to a bigger one, and as the amount of the calculation increases, the accumulation of errors will cause too large enclosures. Then we have the problem statement one. If we give a linear time invariant system described by these two equations, we can find first we define the xk and uk and yk are the state input and output vectors. And the fk is the actuator fault vector. And the noise term and the disturbance are the omega and v in these two equations. These two equations are commonly used in many research. And the other, such as the A, B, E, F, C, and D are constant matrices. And a common way to deal with this system is to combine the actuator fault and the state vector into one novel vector. And then we can construct the augmented system as this one. Okay, in this system, we can see that we have make the fault and the state vector in just one vector. And if we find the xk bar xk, the bottom row of the xk is not 0, you can find the system is in fault. And we define a new index. The delta fk is the fk plus 1 minus fk.
May I briefly interrupt you? Could you go back to the previous slide, please? I think that's a question that is interesting for the remainder of the talk. Is the matrix G bar correctly defined? Because when you
which one?
The matrix G bar, G overline.
G bar. Yes.
Because if you say that delta F is the difference between two Fs, shouldn't this be something depending on capital F?
Okay. the G bar is okay. The G bar is wrong.
Yes, I think there should be a factor F times identity matrix.
F times.
No,
If
it's okay. It's just an integrated disturbance model that you discretized. Okay, now I understand the equation.
Oh, okay.
Yep. Okay, please go ahead. Sorry for interrupting you.
Okay. And then we construct the state interval observer of the augmented system. The method can be also found in another work by Zhenghua in the systems and the control letters in 2018, and also in the another one paper that can be also found in the Wen Tao, also in the systems and the control letters. Okay, we use the method in this talk, and we can construct the state interval observer of the augmented system like this. We define the hat bar xk is the estimated vector of the augmented state vector. And the problem is to find the L, T, and M in this observer. And also we define an error system. The error system is defined by EK equals to bar xk minus hat bar xk. And this is the state, and this is the estimate. And we can also obtain this equation. And now, similar to the previous work by Zhenghua, there is a theorem in this talk. And if we give a scalar, and if there are positive definite matrices of this can satisfy and this equation, and the error system is stable. This can be solved by the LMI method. Okay. Then, if we use the previous theorem, we can have the EK is robust to disturbance and noise, and the main challenge is to reduce the impact of the wrapping effect. And how the wrapping effect occurs, that's because of the interval observer. We can calculate the error interval, but if the time increases, the interval will getting bigger and contains much more unuseful states. So we have this problem that we define the vector set inversion problem. We define X equals this set, and this is similar to the severe operation in the interval methods. The X is a solution set, and the SKB is the vector set inversion interval. That is also called the severe one. And we can have the yk. And in this equation, y, u, and delta f, omega, and v, those three of them are intervals, and they are the output input for difference interval, disturbance interval, and the noise term interval of the given system, and from k and to k plus s. And this is a common way to deal with the severe problem, and we can make these matrices. So if we use a severe algorithm to solve the above problem, we can find the larger the time length s, the higher the accuracy, and the greater, most important, and the greater the amount of calculation. And in this talk, we will we want to find a new way to convert the interval box to the form of row vectors. We know in a matrices we have multi rows, and if we see in this figure, we define some different indexes or vectors. The L is a vector group representing all interval boxes like this in the solution process. And we can have 4 different situations. In this figure, we explain what's the difference between them. Okay, the first one is if the O, L, and Y intersect, but not commonly belong to the Y. And we can find such as the OX0. Yes, this type. The black box is the O, and the pink one is the Y. We can find these 2 sets are intersect, but Y is smaller than the OXK. And the second is if the OLL and Y have no intersection, such as this one, OXK1, and we can find the yellow box and Y have no intersection. And the third situation is the OL belongs entirely to Y, such as the green one. The X2 is here in this box, but if we compare use the OXK2 compared with Y, we can see the OL belongs entirely to this pink area. The fourth situation is OL have partial intersection with Y, and the width of the corresponding interval box is less than the precession parameter, such as the OSK3 and the Y interval. So we have these 4 different situations, and we should analyze on these these 4 situations. We define a test function by the Boolean variables. The Boolean variables is commonly used in the electricity and the computer science. Okay, it can be defined. The output of the Boolean variables are only 1 and 0. we use this idea, we define this test function. We have three different outputs, depends on the situations of the intersection. The first is the in. In is the if the t equals in when OL is in the y, and if the output is out, that means the two sets have no intersection. And the third situation, we have t equals EPS. So before we use this test function, we should make a precision parameter that determines in some degree of this algorithm's effectiveness. Is the epsilon. So before in the previous analysis, we have 4 different situations. Now we use the test function to deal with these 4 situations. The first one is if we have the OL in this y interval, the output of the test function is 1. Otherwise, the output is 0. We have some different feasible sets. The first one is the n. Okay, the first one is n, and the second one is the uncertain vector group U. We define U, and the third one is the whole feasible set. We define the L. The main purpose is to determine all the states in the feasible set L until the L is empty. We determine one and we erase this into different sets. That includes the N and the U. Okay. And we give another theorem that the solution set obtained by the vector set inversion interval filtering algorithm satisfies xv is in the x and the x is in the sk and the epsilon. Okay, the proof is very simple. That can also be seen in the diagrams or the figure. And at last, we give an example. We set some state matrix and input matrix, output matrix, disturbance matrix, and noise matrix, and the fault matrix. And then we use the theorem in Zhenghua's paper, and we can get the T, L, and M. And then we make some simulation tests. We give the initial state and the initial error interval, and we define the unknown disturbance and the noise term, and we give an input. Then we set a fault when k is between 50 and 100. We set fk is 10, and in other time interval, there is no fault in this system. And we can have these 2 different figures. The first figure is to show the fault estimation results. Okay, we can see from the figure and the interval is narrowed by this new algorithm. And in this figure, we show the states x1 and x2 estimation results. At last, we give some conclusions. First is the actuator fault observation method for the linear system with UVB disturbance and noise in this talk is studied. And we use multiple time output data to reduce the wrapping effect of the interval calculation. And in this talk, the proposed algorithm is to solve the problem that the calculation time of the traditional interval free-tuning algorithm increases. And the last vector set inversion interval free-tuning based fault observer can be also extended to some other fields. Okay, thank you for attention.
Yes, many thanks for your presentation. And now I would like to hand over the microphone to the audience to ask some questions. Is there anyone who wants to start?
Maybe I can start.
Yes, please, Tarek.
So thank you for this very interesting presentation. I have two small questions. The first one, for slide 23 for numerical simulations.
Slide 20.
Technique have you made the comparison?
Excuse me? This slide?
Yes, it's mentioned that you have made some comparisons with other filtering algorithms.
Yeah.
With which
the algorithm that we compared with is in the with the Zheng Hua's paper. He published in the International Journal of Adaptive Control and Signal Processing in 2015. The title of the manuscript is Actuator Fault Estimation Observer Design for Discrete Time Linear Pattern Varying Descriptor Systems.
Okay, thank you. Since the model is linear without parameter uncertainties, is it a good idea to do set inversion? Since the solution set is a zonotype which can be easily characterized using the formula you gave. So is it really necessary to do set inversion?
Actually, the main purpose of this talk is to propose an idea to deal with the wrapping effect of the interval observer. And, you know, if we use the severe algorithm, the wrapping effect is also there. We use this algorithm, we can narrow the width of this interval.
Do you think that this technique can be extended to linear systems with parameter uncertainties? For example, if the matrix A is not exactly known, do you think that it's possible to extend the technique proposed here?
I think we can try, but it's hardly to say we can directly use this idea into the other set membership filtering, such as the zonotopes or ellipsoid. I don't think it's surely.
Okay, thank you very much.
Okay, thank you.
Yes, please, Luke.
Okay. Thank you for the presentation. You can hear me, I hope. Yes.
Yes.
So I would like, I think also as Tarek, that it would be a good idea to extend to nonlinear problems, since I do not see why it would not work. But my question is on slide number 12, please.
Number 12.
Yes, in your formalism.
In
12.
12.
Yes, here.
12.
So when you define your set inversion problem, why do you put the set X is a list of boxes, but why don't you write X? For me, it should be a subset of Rn and not a list of boxes, no? Do you understand what I mean? Here you write X is equal to a set of boxes.
Yes.
And I would have defined it as the set of all points of Rn, such that the image by O belongs to the box YK, no?
Yes.
Oh, okay. So yeah, because here you define as a list of boxes, probably. Oh, okay. So it was my yes. So it should be a subset of Rn. Yes. You agree with this? Yes.
Yes.
Okay. Thank you. That's all. Thank you for your answer.
Okay.
Yes, I think I would like to pick up both questions now, the one of Tarek and Luc, especially since Tarek started with the question, is it really necessary to perform a set inversion when the system is linear, time invariant, where you know all parameters exactly? Would it make sense? I think the slide is a good one here, or the next one where you have listed all the matrices. You could refer the current state intervals or sonotopes or whatever to a function that depends on the initial states, just by multiplying each of the system matrix recursively. For example, let's say your state x1 is a times x0. Your state x2 would be a squared times x0. Your state x3 is something like a to the third power times x0. And I think this could, if you're working with some moving horizon of past data, I think this could significantly reduce the computational complexity.
In the moving horizon?
Yes, because this is what you're doing, I think. Your indices here say you take a window of data.
From K to K process.
Yes, and in the case that your system model is linear time invariant, you could represent all the states in the window from K to K plus S as functions directly on the initial state box, state sonotope, or whatever.
Okay.
Why didn't you do this? Or do you think it's just something that makes sense to investigate in the future?
I think, in my opinion, this is one of the common ways to deal with the severe algorithm. So I use this moving horizon, I think.
Yes, I agree with using a moving horizon, because if you have slowly varying faults, this really makes sense to pick up information of several points of time. I think this is out of question. My question is more or less, does it make sense to relate the current state intervals over the complete window to a function of the initial state?
I think it's a good question.
Because this would be something like augmenting your system model once more. Just defining a stack vector that contains the x at point k, the x at point k plus 1, and so on. And you're referring it to the point K. Yes, maybe that's just something yes, to think about for possible future extensions. And maybe before I ask again the audience, one further question related to your slide 16.
Slide 16.
Yes, what you showed there in this yes, pink area is the domain that certainly belongs to the solution set. Okay, you cannot characterize it perfectly by interval boxes, for example, because it's somehow distorted, somehow rotated in the state space. Now, I think I did it last year for a conference paper for the IFIC World Congress. What I extracted from something like such a CVR-like algorithm is using the interval midpoints. And I looked at the distribution of the interval midpoints, how they were distributed in the state space. And I used this directions, how the interval midpoints were located, as some information how to perform a coordinate transformation, something like a principal component analysis, to figure out in which direction it would make sense to rotate the state space in order to more tightly represent the solution set. I think that's an idea what you could do if you want to use a CVR-like procedure. What would also speed up the work.
Okay.
It's just an intelligent guessing of how to rotate the boxes.
How to rotate the boxes?
Yep. Because axis aligned in the original state space is usually not the best way.
Yes. Yes. In this talk, we use the text function directory, the directory in this T function, and we can find the results, different results to determine the situations.
Yep. Do we have any other question from the audience? If not, I can continue. Then we have a look at slide 17.
17?
Yep.
17. Yeah. Oh.
It deals again with this test function and the splitting operator. Currently, you say that all of the boxes that possibly contain solutions, they just get the label epsilon. I think this doesn't prefer anything like boxes that have large amount of overlap, in contrast to those who have very little amount of overlap. Maybe it's a suggestion to use in future work something that is related to the amount of how far the domains are overlapping, because you already computed this W.
Yeah.
And maybe directly using the width of overlap as an indicator, does it make sense to further split the box? Or is it something that is so tiny and has so small amount of overlap that it may not even get any improvement?
Yes, and we should erase the very tiny boxes.
Yeah, and I think this would help not only erasing or ignoring tiny boxes, but also preferring boxes that have a large amount of overlap.
Okay.
Oh, let me have a look at the list of participants. I see Sergei Petrovich switched on the video. Do you have a question? No?
I have a small remark on the terminology. Show me slide 16, the previous one.
16.
the first line, L is a vector group representing all interval boxes. Specialists in pure mathematics know very well group representations and such like things. So when I see vector group representing something, yes, I have some illusions with other subjects in pure mathematics. Understand me? There exists such a concept, group representation. Do you know it? And the first line of your text has obvious allusions with terminology in pure mathematics. L is a vector group representing all interval boxes. So I would suggest to change the term group to something like set, family, or something like this. Yes.
Okay.
You can Google, for example, group representation, group representing. Well, do you understand my remark?
I know. It's about the description of this L. Yeah, the vector group.
So change the word group to something more neutral. Family, set, subset.
That's vector. Okay.
So I have one further question on my list concerning your linear matrix inequalities that you're using. I think the basic concept was something like extending an H-infinity design procedure. Is this right?
Multi-agent?
Your matrix inequalities. The linear matrix inequalities that you used is something like H-infinity.
Yeah.
At the very beginning of the talk, you said, okay, other procedures would be something like also doing pole assignment.
Yes.
And just an idea for future extensions that you could consider. Imposing, for example, from a physical knowledge, restrictions on the domains of resulting eigenvalues as further constraints on this LMI that you already have. Because I think if you know from physical considerations, for example, that the variations of some faults must be very slow in comparison to the system states, it does not really make sense to modify, let's say, the ratio between the absolute values of the eigenvalues in a very dramatic way. And that's something that you could enforce a little bit by eigenvalue constraints. This would be something like pole region assignment instead of pole assignment, not placing hard values, but let's say, okay, we have some subdomain of the unit circle in which you want your resulting eigenvalues to lie. And this would more or less represent some physically reasonable variation rates of the states. That's just some opportunity for fine-tuning the procedure.
Okay. The LMI is the most commonly used in the
yes, and the other thing could also be formulated as LMIs. These were just additional constraints that restrict your solution set a little bit further.
Okay.
Yeah. Do we have any other question? So now I see Peter has unmuted himself. Peter, do you have a question? So no. So if we do not have any further questions, I would like to thank today's speaker again. Many thanks for your presentation. Many thanks also for being so patient to answer all the questions. And yes, I wish all of you a nice Friday afternoon, evening, nice weekend. and we'll see each other again on Friday in 2 weeks. And our next speaker will be Sergei Kumkov from Yekaterinburg, and you will receive the corresponding announcement also in due time for this talk. And have a nice weekend, and see you again soon.
See you. Thank you.
Okay.
Bye-bye.